Okay, we are going to be starting Unit 3, so we're kind of introducing a new topic, and Unit 3 is all about Earth. So now we're going to start talking about things that really pertain more to planet Earth. Chapter 9, oops, it is, your teacher's clicking way too fast. So Chapter 9 only has 2 sections in it, so Chapter 9 is all about Earth and time. Now when we talk about time in science class, we're not talking about time you keep with your watch. When we talk about the planet Earth, this is something that has been here for a really long period of time. So we use a couple of different ways that we talk about time on Earth. The first one is called relative dating. So that is what we're going to do in this first section is 9.1 relative dating. And then 9.2 geologic time is getting a little bit more specifically about actually assigning times to things and then events that have occurred or happened on Earth. The chapter starts out talking a little bit about the history of how we've learned about things that have happened on Earth. In 1666, a gentleman by the name of Nicholas Steno, he was a Danish anatomist, so he studied organisms' body parts. He started to notice that he discovered these stones that looked a lot like shark's teeth. So he studied a shark's head and discovered that these shark's teeth resembled these mysterious stones called tungstones. So really it was his first connection between looking at something in a rock and saying, I wonder if this was alive at one point in time. So that's the credit of Nicholas Steno. A lot of the concepts that we use in geology that we're even going to bring up in this lecture today were really based on Nicholas Steno's idea. So really instrumental in the field of geology. So Steno noticed these tungstones looked a lot like shark's teeth, so he maybe thought, hey, maybe these are shark's teeth, right? Not too far of a stretch. So like I just said, a lot of his theories led to many of the basic geological principles that we use today. And what I should have introduced with as well here is just that idea, that concept, what is geology? So when you guys see that prefix geo means earth. So geology is essentially the study of earth. So if you're a person who becomes a geologist someday, you're going to be studying really any of the concepts that we talk about in this class. So relative dating. Steno's principles are used by geologists to determine the age of fossils and rocks in a process called relative dating. So this is what relative dating is. We put things in an order of events in which they happened. So it's not me saying this is exactly this far old. Relative dating is saying this happened first, this happened second, this happened third. So if you look at this picture here, this really simple picture, and you saw this in the road, ask yourself, what are the order of events that happened? So what happened first? Snowed, right? So it had to have snowed outside, first order of events. Then it looks like we have two other events that occurred. We had a car that went by, and then we have a footprint. So now ask yourself which one happened last. Tire tracks, right? Because if the footprint happened last, you would see that footprint going over the tire tracks. Interesting thing is a lot of these basic concepts that we are using here in our head to sort of logically figure out what happens in geology. Same sort of reasoning that we use if you want to become a crime scene analyst someday when you're trying to work through, what happened first, second, and third. But if you're talking to a geologist, relative dating is what happened first, what happened second, what happened third. Another very well-known geologist was James Hutton. So he's a little bit later, you can see here, 1726 to 1797. He really is considered what most people say is the father of modern geology. A lot of the things that he discovered are really still used today and help us discover things. One of his things that he really focused on was using present findings to describe past geological events. So if we think the Earth is about 4.5 billion years old, we don't have record pictures, people who wrote things down 4 billion years ago, 3 billion years ago, 2 billion years ago to figure out what happened. So he kind of came up with this really basic sort of common sense idea that the present is the key to the past. If I have a rainstorm that happens, and let's say you get tons of flooding in an area and that water is going to move over the land in a certain manner, you can study it now, Why would it be any different if it was a billion years ago? Is water going to fall differently over land a billion years ago than the way it does now? So he came up with that fundamental idea: the present is the key to the past. So even though we don't have records of things in the past, we can use that philosophy. If we see something happening now, we can assume that's the way it's always happened. And we call that, there's this really fancy name, the principle of uniformitarianism. Look at the word that's sort of embedded in there, uniform. If something is uniform, it's same. So if you guys just sort of equate those two things together, so uniform, same things happening today have always been happening. So the principle of uniformitarianism states same geological processes happening today have been occurring in the same manner since the beginning of time. Why would it be any different? A couple of the, I don't know what words we would use for that, basic concepts that we use. This is one of the ones Steno developed, was the principle of superposition. Once again, it's a long word. Superposition, position of items. The bottom layer of sedimentary rock is older than the layer on top. Or another simple way to say principle of superposition, younger over older. The picture on the upper right shows you this analogy of newspapers. So let's say I get a newspaper every day. I'm going to throw that newspaper in the stack, and then tomorrow I'm going to put it on top, and then the next day I'm going to put it on top. So if you wanted to, someone said, hey, grab me your oldest newspaper you have, you're going to go to the bottom of that stack of newspapers. Makes sense, right? Nature is going to do the same thing when sediments are laid down in sedimentary rock. The sediments on the bottom get laid down, then the next layer, then the next layer, then the next layer. So if you're looking at this rock cross section here that you guys see on the bottom, if I want the oldest rocks, I'm going to go to the bottom layers. If I want the youngest rocks, those are going to be the ones on top. Now notice I said sedimentary rock. It's got to be sedimentary rock. So that is rock that's been formed by sediments that get compacted and cemented together over millions of years. When we start to talk about other rocks, it gets a little bit more complex than that. But for sedimentary rocks, it's really that easy. So principle of superposition, younger over older. So here's just another picture just showing us a nice little simple diagram. Oldest layers are going to be on the bottom. Newest layers are going to be on the top for sedimentary rocks. Another thing Steno developed is called the law of original horizontality. All these big things we get in geology. Once again, look at the words that are buried inside there. Original, horizontal. Original, horizontal. Think about what horizontal means, right? Horizontal means when sediments get laid down, they get laid down in a horizontal manner, just like you guys see in the picture there with the crayfish and the fish there. They get laid down in a horizontal manner. So what that means is if you're in nature and you see sedimentary rock that isn't horizontal, something happened to it. It's kind of a big clue to you that something happened that made this rock to be no longer horizontal, and now it's facing in another direction. So the law of original horizontality, sediments are deposited horizontally. Lateral continuity. So lateral is similar to horizontal. You can see their names are right there next to each other in the definition. And continuity, if something is continuous, it's going to be the same, right? Lateral continuity. Horizontal layers of rock are continuous. They're going to be in a straight line. What that means is if they're not in a straight line, something happened. So if I look in this picture here, so this is sort of a cartoon drawing of the Colorado River, which has been wearing its way through the Grand Canyon for millions of years. You will notice when you look at pictures of the Grand Canyon, you have all these horizontal layers that match up on either side, but you're missing a spot in the middle. So lateral continuity is just telling us at one point in time, they were connected and something has come along and caused that rock to wear away. And that, in the case of the Grand Canyon, would be the Colorado River. So lateral continuity, they were at one point in time connected. If I see that there's a space there missing, obviously something happened. The picture on the bottom is actually showing you what happens when a fault occurs. So a fault is a crack in Earth's crust. At one point in time, you can see those layers must have been matched up. If they're not matched up anymore, something happened. When we look at layers of rock, when things come in, and I'll say this in an unscientific way, mess them up, you see they're not normal anymore, we call those things cross-cutting relationships. They're cutting into events that have already happened. So cross-cutting relationships are geologic features that are occurring in rock layer sequences, and they are always going to be younger than the rocks that they cut through. They have to be younger. Those rocks had to have been there first in order for them to happen. It's kind of like if you eat a piece of cake. The cake had to be sitting there before you take a bite out of it. So two of them that you see in the picture here, E marked on the diagram is a fault. So anytime you guys see in these pictures a big straight line, that's telling you that's a fault. So that's a crack in Earth's crust, and you can clearly see how that rock moved. Letter D is called an igneous intrusion or an intrusion. An igneous rock is formed from magma or lava. So underneath Earth's surface, magma in this area came up and it went through all of those sedimentary rock layers and it made new rock. Those rock layers, layers C, D, and A, had to have been there in order for D to come through and reach through those. So cross-cutting relationships, you'll either see an intrusion like you see in the last one, otherwise on the right-hand side, those things, they're specially called an inclusion. Sometimes the rocks get heated to an extent, or pressure goes to a certain extent, so that you're going to get different rock formations looking like you do see on the picture there, but those would be considered younger. So you'd see the newer rock and then the older rock there. So based on all of these things that we just talked about, if you're given a diagram like this, you should be able to start almost like a puzzle piecing together what happened first, second, third. And we're going to practice these in class, so we should kind of be good at these by the time you guys get these lecture notes, because we will have practiced them in class. But you can start to see now, oh, okay, there's that fault. That fault came through, those rock layers had to be there. That letter A, usually anytime you guys see those little dash marks that look like sprinkles on a cupcake, those are an inclusion. So that's an igneous inclusion. That igneous rock came up through there and made new rock. So even though it looks complicated, I can't suggest enough to write things down, write down what you know, and then kind of like piece it together as a puzzle. So we can assume we have the older things on the bottom, but when it comes to igneous rock, that is not always the case. That can come in after the fact. The last part of the chapter talks about fossils, and we're going to talk even more in detail about fossils, but we're going to get them out of the way for notes here. This first thing is called the principle of faunal succession. So flora and fauna, you may have heard of that before, right? Fauna has to do with the animals. So flora is the plants, faunal is the animals. So faunal succession, animal succession. Fossils can be used to identify relative ages of the layers of a rock formation. So organisms found in top layers are going to appear after the organisms below them. So if you look at this sort of cartoon type picture here, I can see in the very top layer, I have an organism that looks similar to a human being. In the middle looks kind of like a dinosaur. On the bottom there, those are organisms we call trilobites. So if I were to come across this rock sequence with fossils in it, I would assume that the dinosaurs were on Earth before humans. The trilobites were before dinosaurs. And just that sort of like common sense approach to, if that fossil is found in a layer below, it's going to be older. That's the principle of faunal succession. So faunal animal succession, orders in which they come in. So here's another thing. So if I have a rock layer sequence and I see all these fossils that are in there, the fossils that are in the lower layers are going to be older than the fossils that are in the layers near the top. When we talk about how fossils form, it's kind of a really unique way that fossils form. They can't just form anywhere. You have to have conditions right where that organism is going to be buried with sediment. So it can't be preyed upon by other organisms. You know, if you have other things that are coming and eating it, organisms that fall into water, it's a great situation for fossil formation, get covered with that sediment. The soft tissue in the animal is going to wear away. So if that animal has muscle or skin, those things are going to go away. All that turns into the fossil is usually the hard part of the animal. So you're talking about the bones or the teeth in the animal. And then over time, as you can see in this picture here, so let me just read through here. So soil is deposited and covers, they're using a shark here as an example, the dead shark. The shark is covered with soil, the soft parts start to decay, so like that muscle and that skin that I talked about, The environment's going to change. Maybe there's not water there anymore. That sediments can be buried for millions of years. Eventually that topsoil can wear away. And then now you're left with the rock that has the fossil that's inside of it. The great thing about fossils is they give us a clue to things that happened on Earth that we would have had no idea that happened if we did not have that evidence in rock. So fossils provide evidence for how Earth's surface has changed over time. We're going to get more into this too. Scientists map fossil locations. So based on where we find fossils, we can help figure out what climate was like in those areas. So if you're in somewhere that's cold right now, let's say you're in Antarctica, and you discover a fossil of a fern. This one's called Glossopteris. It's a seed fern. It actually was found in Antarctica. Clearly it had to have been warm there, right? Ferns don't grow where it's really, really cold. So fossils not only tell us what organisms were alive, they can also clue us into things like what climate was like on Earth here. We're going to get into this later on here, but just showing us, this is a map showing us where certain fossils are found on Earth. And knowing what we know about these animals, we can kind of piece together and actually learn a lot of things about how Earth has changed since it came into its existence. So most of the land on Earth was actually part of a really large landmass called Pangaea about 250 million years ago that you guys see on the map here. And we have multiple pieces of evidence that clue us into this, but fossil location is one of the big ones that actually clue us into it as well. Finally, we use index fossils a lot. So an index fossil, just like if you're going to use an index in a book, it kind of helps us find our place. Index fossils are fossils that were widespread on Earth. They were found in a lot of places, but during a very specific time period. So let's say you find, a rock that has an index fossil in it, and you're like, I wonder what age this rock is. All you have to do is look up when was that index fossil alive, and you know that is the date of the rock. So index fossils can be used to tell relative ages of rocks because they act like an index in a book, just like an index in a book does for us. So here's some common index fossils, just to touch on a couple of them here. Let's pick one in the Jurassic period there. Your teacher's not going to attempt to say that right now. But if I found that fossil, I would know, because it was only alive during that time in the Jurassic period, and I found it in a rock, that is how old that rock is. There's no way I can sit and guess, maybe that rock came from the Devonian period. No, it had to have come from the Jurassic period if it has that index fossil in them. So index fossils are great for helping us try to date rocks. So remember, when we're talking about relative dating of rocks, all we're saying is younger over older. So what event happened first, what happened second, what happened third, that's what relative dating is, not actually assigning an age to it.